Hi, Year 12s. Welcome back to Chapter 13, Dynamics. Previously, we looked at the second law of Newton with application when you have a variable force and resolve that using a technique of anti-differentiation. Now, in 13F, we're going to look at equilibrium. Is the situation when the resultant force is equal to zero. And what it means is, in English language, you will see the term equilibrium. Okay, so just be mindful every time you get a problem or a worded question, as soon as you see equilibrium, this is a situation you need to you are dealing with, and then you will have different strategies you can resolve and find the values of the unknown. To describe what is happening when the particle has zero acceleration is the particle is at rest and it will remain at rest, or the particle is then moving, but what it means is as it has zero acceleration, it will have a constant velocity. With equilibrium, we're going to concentrate on the first part when the particle is at rest. Triangle of forces. So when you have a situation when the particle is submitted to three forces only, and it is in equilibrium, those three vectors, and if we can we rearrange them so that they'll form a sum, and the sum of those three vectors will be a null vector, and that shape now that you form is a triangle, and we're going to use some properties of triangles. There's two rules we can use. First, we're going to look at the cos rule, and the next one is kind of an application of the sine rule. Okay, those are the two sort of short techniques for you to resolve the situation, and at last we'll see the general method, which is a vector resolution in the Cartesian plane. Always attempt those two, the first two techniques, which is the cos rule and the application of the sine rule. With the cos rule, so we look at a particle in equilibrium. It has three forces applied to them. We know their magnitude, but notice we don't know the direction. But because it's in equilibrium, those three vectors must be equal to zero when you move them around to form a triangle. So first you will need to do a sketch, and then you need to find the angle between those two vectors. So you draw randomly your forces, okay, and from part B it tells you need to find the angle between 2 Newton and 4 Newton forces. So what you do is you draw your angle here, and that's your unknown. Okay, so every drawing might be slightly different considering the lack of information that you have here. With those three vectors, you turn it into a triangle of forces. So what you do is you pick one vector, let's say you keep 2, and you're going to translate 4 and 5. So you translate 5 to be here and 4 to continue, and you can see you're forming a loop, and that equals to the null vector. Okay, and then you recalculate that angle in terms of theta, which is inside the triangle, which is your supplementary angle, and you can apply the cos rule. So applying the cos rule, and again you use the angle inside the triangle, you resolve it, you find your 180 minus theta, you can determine theta, and that is your answer to 2 decimal places in degrees. Okay, reminder, when you do inverse of cos, make sure you have set your calculator in the right degree mode. Alright, Another example. Okay, so you have three forces applied to it. You know the angle between two, and the unknown this time is one of the forces that we call the force P. What you need to do is do your triangle of forces. So you have your original force. So let's say we keep that 3 Newton in. You you translate the 4 Newton over here, and you translate the P. So now you have your triangle here. As you know, this is your 120-degree angle. Those two vectors are identical and parallel. It means dot two angle are co-interior. So that side has to be 60 degrees because both of them add up to 180 degrees. So do remember, even if we learn new skills, there's past skills in terms of geometry with shapes, parallel lines, triangles, or any sort of shapes. You need to apply those skills to determine some unknown angles. Then again, we have that triangle. We can apply the cos rule because that's all unknown. Hence, we have that formula. We simplified and we get the magnitude as square root of 13 Newton. Okay. Now, again, you have three forces. It's an equilibrium. Now the situation is you know those angles that will add up to 360 degrees. Once you know, yes, they all three add up to 360 degrees. If you only know two angles, it's enough to find the third. What it means in this situation, it's more efficient to use what we call the application of the sine rule. Okay, and that is the formulas that you get. So you get three equations, and that could allow you to solve a system of up to three unknowns. Okay, so let's continue with that. Notice the letter of the angle is matching the opposite name of the vector force, and here it will be the magnitude of the that force. For this example, we have again three forces in equilibrium. We have two unknown forces. We know all the angles and one force. We apply the application of the sine rule or the Lami's theorem, writing the rule, and you can see you have enough equations to find the value of P and Q, and you resolve that using a calculator and hence decimal answers. Alright, resolution of forces is the general method to solve the situation of equilibrium. Again, you have three forces. They express in Cartesian form. You have your resolution in the direction of I and j for all the vector forces. Because it's an equilibrium, the vector forces added together will equal the null vector. It means that respectively, if you project in the I direction, you have the I component sum will be equal 0, and the same for the component in the j direction. Okay, so for coplanar force, coplanar means they are in the same plane. We can show that the resultant force is 0 by showing that the sum of the resolved parts in each of the two perpendicular directions is 0. Okay, so this example, here you could use the Lami's theorem to solve it, but here we're going to use the resolution in the I and j direction. So express all the vectors in terms of I and j. So you're gonna have to kind of narrow down the angles. You draw your horizontal line to find your angles in terms of either the x or the y-axis. And as you project respectively, you project in a j direction that needs to be equal 0. Okay, you project as well in the I direction, which is also 0. Therefore the sum in both directions is 0, so it is in equilibrium. Alright, now you have a situation where this is where you can use also the Lami's theorem. So you have two unknown forces. You will know two angles. As you know two angles between two vectors, you can find the third angle, and you will be able to apply the Lami's theorem. Alright, as we project in the respective direction, we end up with two equations equal 0 in terms of P and Q. Those two equations are simultaneous linear equations. You can enter that on the CAS calculator and solve for P and Q, or here if you were to use it, solve it manually, you can see that the second equation here only has the Q unknown, which we rearrange to make Q the subject, and then we substitute that value into the first equation, make P the subject, and we end up with that answer. So those answers are to 2 decimal places, and it will be in newtons. And that's it for 13F. See you later.